How's it going, folks? Jack here with another reaction. So many of you have requested that I check out the second part, or at least the Cursor unit video, and I will of course oblige. I've been awaiting this one because the first one was absolutely amazing. I was left flabbergasted with the last unit that we had to deal with, which was quite a notation to give in a report, but I mean, it's not always that you need to simplify units to make it look good on paper, because there's clearly something that you need to show. If it's the relation between two different dimensions, or these values or units, it's important to leave it in the way that it is. So I kind of understand that. I've done that in the past as well. Sometimes simplifying things is not the best idea. But one thing was not cursed in the last video, which was the music, which I was led to understand that he makes himself, Joseph that is, and that's absolutely great. And some of you actually wondered if I was doing the same thing while reacting to the video, because I have a tendency of like matching the soundtrack when commenting, just to keep the flow of the video going. It's not always easy to find those because I don't always, I listen to a lot of music first and foremost, but I don't always capture the right one. But I do not compose my own music either. I do find them online, or at least find something that is approximate to the thing, because piano is something that I unfortunately will never have the patience to play. I do play bass, that's one thing. Piano is just not my thing. Like whenever I come across a piano or keyboard, I just literally end up goofing around, playing stuff like "Oh My Fellas." So yeah, that's not my thing. I was in fact using a soundtrack for the game Untitled Goose Game. So if you want to try that one, highly recommend it. It is chaotic and quite cursed of a game to play. That being said, let's not waste more time and let's jump straight into the video.
After posting my previous video on cursed units, and after it got a massive spike in views for no discernible reason, I discovered that kilowatt hours are extremely polarizing.
What's good?
A lot of commenters argued that kilowatt hours was a perfectly sensible unit for ordinary people who measure their appliances in watts and hours, while the alternative unit, megajoules, is much less intuitive. But there were also a lot of other commenters who sympathized with me, saying they had given the same arguments to their friends and family and were treated like lunatics, and that the oppressed joule appreciators should rise up against cursed units.
Okay, listen. If you're a joule appreciator, I might as well just change everything into calories. Why not? I mean, why not switch to the way more superior electron volt? God, I love that he was using the Giga Chat soundtrack too. This man is great. It's not that deep, guys. It's not that deep.
The truth is, I actually don't feel strongly one way or the other. I just find it fun to play around with notational standards given to us by history and make a caricature out of it. My goal is to teach you something about mathematics, not to claim that these are signs of societal dysfunction. Wait a second. People were saying they've seen kilowatt hours per 1,000 hours. Isn't that just watts?
Yes.
Wait, I need to check this for myself.
Come on. Here we go, mocking Europe.
Europe! The best explanation of this I've found is from a user on the Electrical Engineering Stack Exchange, who suggests that for a long time people conflated wattage with light bulb brightness. This meant that when converting from older incandescent bulbs to more efficient LED bulbs, someone might swap out their old 40-watt lamp with a new 40-watt LED lamp and get flashbanged.
Sorry for that, I have forgotten to turn off my phone's sound there. And one comment that I can give about this one, I studied building and engineering for 2.5 years before switching to physics, and well, it had to do with how to construct building and houses and a hell of a lot of other things. With that, you have to take into account such things as the U values of things, such as glass, and their R value as well. The U is the amount of heat that gets through. R, of course, stands for refraction. And with that, inevitably, you also have to deal with lumen. That being said, very few people cared about lumen. So it's not very often that you encounter that. So in all fairness, I can give it to people that they decided to go with just talking about wattage when it came to brightness instead of the actual value that is referring to it.
So manufacturers describe the brightness in watts and the efficiency in kilowatt hours per 1,000 hours. This, of course, would never have been a problem if anyone cared about lumens or candela, the actual units for brightness. But you know what? It simplifies nicely, so it's not the worst. There's also kilowatt hours per annum, which is what my fridge has. That's seconds, hours, and years all in the same unit. You know what else was polarizing in the last video? The music. And I intend to keep it that way.
Nice.
Anyway, here's some more cursed units.
Oh, organic
The
chemistry.
radian is a unit of angle such that 360 degrees is equal to 2 pi radians.
Sorry, I saw the logarithm, or at least the log value there, and immediately my brain went, no. While obviously not everything is organic chemistry in chemistry, it's kind of difficult to avoid, especially when you are, like me, want to just take a course that is perhaps not the most interesting just because you're kind of done. So they decide to go with statistical physics, where it is almost impossible to not deal with either reactions, the energy states of things, which will require you to deal with a lot of that. Let's go back a bit.
The radian is a unit of angle such that 360 degrees is equal to 2 pi radians.
Yeah.
This is so that if you have a circle with a radius of 1 unit of length, let's say 1 meter, then an angle of x radians subtends an arc length of x meters along the circumference. That's pretty neat, and what's also neat is that if the radius of the circle changes, then this arc length changes proportionally. So we could think of a radian as being 1 meter of arc length per meter of radius. A meter per meter. So a radian is just 1.
Yeah, dealing with dimensionless units have a tendency of... It works well initially, but you kind of need to... we have an expression in Danish, like to keep your tongue in your mouth, because it can easily go in weird directions.
When units completely cancel out like this, we call them dimensionless. Radians are quite special here. If we used a different measure of angle like degrees, we would get a different number. The fact that the radian is the unique angle that gives 1 is the reason why in mathematics we commonly assume that everything is in radians and don't write any units for angle at all.
Then comes
This has
electrodynamics.
some weird run-on effects. There are angular versions of momentum and force, which are
Yep,
called
angular
angular
momentum.
momentum and torque.
Yeah.
And since these depend on the radius as well, they pick up an extra unit of length. If we continue ignoring radians, then
Joules.
torque inexplicably has the same units as energy.
Oh god. Seeing the joules here reminded me how I mentioned electron volts before, and if we start talking about radiation, we are about to enter in some fun territory.
There's also a 3D variant of radians. A steradian is a solid angle subtending an area on the surface of a sphere equal to the square of the radius. So, by the same reasoning, steradians should be measured in square meters
meters over
per
meter squared.
meter squared, which is a different thing, but also the same thing. But are radians really dimensionless? I don't think so, because there's another conflicting way that we could make angles dimensionless. Just take the number 1 to be 1 revolution. This is the more sensible option for describing the frequency of something rotating, where we use units like RPM, revolutions per minute. So we have 2 different standards, which are off by a factor of 2 pi, and this results in 2 pi's popping up all over the place in any equations relating to rotation.
Just like dimension analysis is an entire field of its own, when you first start studying anything related to physics, the mathematics part will have you deal with such things as a unit circle, which is very important because this one has the length of 1, and everything in there, you need to like know the coordinates of how everything is separated and how to deal with the imaginary part of set circles and set coordinates, and also give in the real part. This also becomes super important when you have to write some things like partial differentiations, where you actually need to make guesses. Yes, there is a part in math that actually involves guessing. Had to pause the video there for a second to show you what it looks like. These are my notes, very colorful, because yeah, when you have first year university brain, you kind of need to feed it with a lot of dopamine, make it focus on the stuff that you're actually making. But yeah, it basically involves such things as having partial differentiations on different levels, and you then giving a gas, which is the word here in Danish, and a particular gas to what can be the complex solution to your equation. But I know some of you are already saying, oh, keep saying your wonderful words, magic man. But the point I'm trying to get at is that in order to even make such guesses, you need to be very well versed with a unit circle and learn how to navigate with those 2 pi movements, so to speak.
So angles aren't really dimensionless, we just like to pretend that they are. But now let's look at a unit that is dimensionless, but we like to pretend that it isn't. A mole is a unit of quantity equal to the number of atoms in 12 grams of carbon.
Yeah.
If you're thinking, isn't that just a number? You're correct. It's called Avogadro's number, and it's approximately 6 times 10 to the 23. Despite the fact that the mole is very clearly dimensionless, it's still counted as an SI base unit. The perpetrator here is chemistry, and when it comes to shoddy units in chemistry, trust me, the mole is the tip of the iceberg. First, let me state that while you can multiply, divide, and take powers of units, more complicated functions like exponentials and logarithms only apply to dimensionless quantities.
This man is basically going in every direction that I would like to go when talking about these kind of things. That's awesome. This is the probability of, or usually just called the Gibbs factor, i.e. the probability of finding a potential at a given energy state, where the ES obviously here is your energy state, K is a given constant, T is the temperature, and Z down here is the Gibbs sum. Again, paused a little bit here to show you some of my notes. This is essentially what it would look like normally. And yes, the Gibbs factor is given in this way. Normally, like you have an N and a EU here to give the right state, where you have to give the probability that the system at chemical potential mu and at temperature tau is will have n particle and will be at a quantum state as and that given energy level. So usually this is how you are going to be expressing that, and this is what Z truly looks like. This is, by the way, also called the Boltzmann distribution, which should not be confused with the Maxwell-Boltzmann distribution, which is something completely different. And to keep it simple, it just has to do with the prediction of how a system will be at a given energy state. So I hope that this is understandable for you. Predicting work, statistical physics. That's the part of it that I was talking about before.
You can see this in complicated equations in other areas of science. The units have to cancel before we can apply weird functions to them. After all, it doesn't make sense to take the logarithm of a liter, right?
Yes,
Except
pH.
That's exactly what pH is. The acidity of a solution in water is determined by the concentration of hydrogen ions. You need to measure this in moles per liter and then take minus the base 10 logarithm of that, and that's the pH. So what's actually going on here is that we're secretly dividing by a constant 1 mole per liter to make the units work out. And this is very important, because if we measured the concentration in different units, we'd have to convert this 1 mole per liter to those units as well. This is why the whole study of dimensional analysis exists. When you conflate units, you get the wrong results.
Zepto.
Chemistry literature has a bad habit of randomly forgetting figures of moles per liter, which...
I'm sorry for pausing there. I know it might be a little bit annoying, but what is zeptoliters again? Okay, I need to look this up. Metric prefixes. What do we have? Zeta is... Oh, so it's 10 to the 21st. Jesus. Iota. Queta. Rona. Okay.
Which makes the dimensional analysis really annoying. This all culminates in the reaction quotient, a quantity which, by some interpretations, has different units depending on the chemical reaction.
Heat.
Now, apparently the pH of pure water is 7, and this figure confused me for a long time. pH is determined by the concentration of hydrogen ions in a solution, but surely pure water doesn't have any ions, right? Well, as it turns out, water self-ionizes, meaning water molecules randomly split up into ions and then randomly recombine. The presence of these temporary ions is what gives water a pH of 7.
I see.
But why 7? What's special about 7? Wouldn't that change with temperature or pressure?
Yes.
Well, it turns out the pH of pure water is exactly 7, when the water is somewhere around 24.87 degrees C.
Ah, okay. So it operates in the same manner as specific heat capacity and latent heat capacity and all of those things that are measured at specific temperatures. All right.
So the choice of 7 as neutral is completely artificial. Going back to moles, the fact that we use a special unit for what's actually just a number isn't too weird. It's quite common for two units with the same dimension to behave differently because of context. For instance, hertz and becquerels are units of frequency that are both equal to inverse seconds.
Yeah.
The only difference between them is that hertz is used to describe periodic processes like waves, where the time between each event is the same, while becquerels is used to describe random processes like radioactive decay, where the time needs to be averaged over many events. They're
forgot
technically
that.
the same unit, but they have different contextual meanings, and so you would never conflate them.
Yeah.
Now, becquerels originate from the study of radiation, and radiation dosage is another situation where you have multiple units with the same dimension measuring incompatible things.
Oh my
Grays
god.
and sieverts both have dimensions of joules per kilogram, that is, radiation
Absorbed.
energy per unit mass. But
Yeah.
the former is absorbed dose, which is simply total energy, while the latter is equivalent dose, which has an extra factor depending on the type of radiation to describe how much it damages living things.
Oh, okay. Oh, okay. Now, that makes sense. Because a gray is more or less the same as a rad, right? Rads are just 0.01 grays. And, well, it's joule over kilogram because a rad is usually given as meter squared over second squared. So, yeah, you get that. Yeah, it's just joules over kilogram. Okay, yeah, that makes sense. But then we of course have other stupid units such as the rams, curie, which is not very used anymore, named after the lady who quite literally found it, at least died doing so with her husband, Marie Curie. The becquerel, as was mentioned there. Röntgen is a fun one because my dad carried a certain dislike of like German things, but his grandma left him with a radium clock. And he could not stop talking about that thing and talk about how the Röntgenstrahlung, the Röntgen radiation that came out of it was affecting them. It's kind of grim, like shit. They had those things just because they were fluorescent at night, and it was beautiful to see those light, but I don't think he kept it. Last one is my favorite, of course, the electron volt, because it just has all to do with ionized radiation, everything that can rip an electron apart from the atom. So why not just use the electron volt? It's wonderful. It literally coincides perfectly with the the elementary charge of an electron. So use that. As you can tell, I am very fun at parties.
Again, these units have the same dimensions, but you can't just interchange one for the other. However, the study of radiation does also have some redundant units. A rad, for example, is 1/100th of a gray, and they both measure absorbed dose.
Yeah.
We could have just called the rad a centigrade, but no, it gets its own special name. The historical reason for this is the separation between two competing systems of units, the SI system and the CGS system.
Oh, fuck.
This is a whole can of worms.
That explains the dine.
A can of worms that deserves its own section. CGS is a system of units based on the centimeter, gram, and second.
seconds.
It was an old attempt at standardization that was eventually supplanted by the SI system, which instead established meters and kilograms as the base units of length and mass.
Wherein we now have a total of 7 units that make up the SI unit, and I think a little bit more. But just imagine how crazy this has to be to convert everything down to centimeters, grams, and seconds. You can do that, but it becomes messed up. Like, how are you going to explain everything when it comes to electrodynamics? Like, okay, we could do that. No, you can't even do that with the radiation that we just dealt with. Oh my god, this is... no.
But the usage of centimeters and grams is not the biggest difference between CGS and SI. The biggest difference is that while the SI system now has about 7 base units, CGS insists on describing everything in terms of centimeters, grams, and seconds, even when it reasonably shouldn't. This causes a big problem with electricity. First, I need to give some background on how we measure electricity. There's two ways that we could connect it to length, mass, and time. The first is to look at the electrostatic force between two charged objects. This force is modeled by Coulomb's law, which we can use to define the coulomb, the SI unit of charge. The second is to look at the magnetic force between two current-carrying wires. This force is modeled by Ampere's force law, not to be confused with the two other laws named after Ampere, which we can use to define the ampere, the SI unit of current.
Everybody who's dealt with electrodynamics right now is furiously throwing out gang signs trying to figure out which way they're supposed to be turning their hands.
Now, current is just moving charges, so we want to define these in such a way that an ampere is just a coulomb per second. 1 coulomb's worth of electrons traveling through a wire every second. In order to do that, we need to introduce some physical constants to make the units work out, called the electric permittivity and permeability. But CGS works differently. In CGS, there are no constants, because everything is centimeters, grams, and seconds. The CGS unit of charge is the Franklin, also called the stat coulomb, which is the charge on these objects such that if they are placed 1 centimeter apart, then the force between them is 1 dyne, the dyne being the derived unit of force in CGS. Rearranging, we get that 1 Franklin is a centimeter times the square root of a dyne. This approach is called electrostatic units, or ESU. Meanwhile, the CGS unit of current is the BO, also called the abampere, which is the current through these wires such that if they are placed 1 centimeter apart, the force between them is 2 dynes per centimeter of length because for some reason physicists have an obsession with throwing factors of 2 around.
Wait a second, I'm sorry, I'm a little bit puzzled there. BO. I was thinking about Boyle-Mariotte law, but that has to do with heat. Oh, Biot-Savart. Yes, that's the one. Okay, perfect. It makes perfect sense with the permeability that was showcased before. Okay, yeah, a Frenchman who made this law and apparently also is responsible for this mess.
Rearranging, we get that 1 BO is just the square root of a dyne. This approach is called electromagnetic units, or EMU. Okay, we now have CGS variants of the coulomb and ampere. We know that an ampere is a coulomb per second, so naturally a BO should be a Franklin per second, right? Well, no. The units don't work out. A Franklin per second is a new unit called a stat ampere, a dyne to the half centimeter second to the minus 1. And a BO second is a new unit called an ab coulomb, a dyne to the half second. That's okay, it just means that we need to multiply by some constant in order to get between these two schemes.
But you can't do that.
This constant must have units of centimeters per second, which means it's a speed.
Oh, the speed of light.
Can you guess what speed this is?
The speed of light.
It's the speed of light.
Okay, this guy is awesome. It should continue telling stories like this. I was at the edge of my seat.
This fact was discovered around the mid-1800s, and no one could make sense of it since the entire study of electricity was in a serious state of disarray, probably in no small part due to the confusion between the two variations of units I've just described. This was eventually disentangled in a series of papers by James Clerk Maxwell, who connected all of the results of the findings to a single theory, which we now call Maxwell's equations. Using this theory, Maxwell derived a model for a wave of propagating electric and magnetic fields, and derived that the speed of this wave should be this ratio between the static and magnetic units.
Which was
by
very
this point in time
close.
had been measured to be very close to the speed of light.
Yeah.
It was already well known that light had wave-like properties, so this was the smoking gun that confirmed that light was in fact an electromagnetic wave. Now, that's a fascinating bit of history that's totally not cursed, but what is cursed is that the speed of light is 300 million meters per second. Sorry, CGS. That's 30 billion centimeters per second. Which means the two variants of CGS are different by 10 orders of magnitude. This massive disparity of scales is part of what makes electricity so counterintuitive. I think this is at the core of why electric quantities have all sorts of special names, unlike, say, velocity and acceleration, which are always expressed as derived units. In addition to amperes and coulombs, we have volts for voltage, ohms for resistance, farads for capacitance, henries for inductance, Webers for magnetic flux, and Teslas for magnetic field strength. And each one of these units can be thought of in about 10 different ways.
What I think from my realization there with BO, right, with the Biot-Savart law, is just that we have a bunch of people who just wanted to have their names given to the different units. That's all there is to it. I cannot see a reason as to why we couldn't just be stuck with actual constant. Like, fine, call this a Tesla. Keep it at that, okay? As I said before, there's nothing more badass than having a unit of measurement called after you. That's dope. But also, don't make it difficult for the rest of us. Like, if you are Mr. B.O., do not, and I repeat, do not do this.
To be honest, I respect the boldness of CGS, trying to reduce everything down to 3 units. It reminds me of Planck units, where you define the speed of light to have a value of 1, so that length and time collapse to the same dimension. And then you do the same with 3 other constants, and as long as you're consistent, you get a system that's entirely dimensionless numbers. These are pretty useful for simplifying calculations in certain parts of physics, but be careful because if you pick different constants, you get different results.
Yeah.
CGS has for the most part been supplanted by SI, but it's still quite common to see centimeters and grams being used in a couple of smaller fields of science that like to bask in their old-fashionedness. Which leads me, of course, to materials science. I'm going to build for you a unit that only a couple of people suggested in the comments of the previous video, because only a couple of people know about it.
A bara? What the hell? I mean, I saw, from what I can see here as well, we have Quicksilver, or me being the only one calling it Quicksilver, Mercury. So we're dealing with some temperature changes with pressure. What is this?
This is going to be a unit for describing a property of a substance. So before I go into it, just as a warm-up, let me go through the example of heat capacity. Specific heat capacity is measured in joules per gram degree C. So, given a certain number of grams of a substance, how many joules of energy do we need to put into it to raise its temperature by a certain number of degrees C?
4.18 for water. Literally the only one that I remember.
Each substance has its own number attached to this unit. For example, water has a heat capacity of 4.18 joules per gram degree C, while tin has a heat capacity of 0.21 joules per gram degree C. Make sense? Okay.
Yeah.
Let's now build a unit to describe the diffusion of gas through a substance. How easy is it for air to get through a membrane? Well, the amount of air that gets through can be measured as a number of molecules, so we'll use moles, right?
Right.
I'll use moles for now, but we'll come back to this later. The next thing to consider is surface area. The bigger the surface area of the membrane, the more air can get through.
Square meters.
Let's measure this in square centimeters. So our unit is now moles per square centimeter. Make sense so far? The next unit is time. If we keep the air pressure on each side consistent, air will flow through at a uniform rate. So our unit should be in moles per second per square centimeter. Okay. The next unit is thickness. The thicker the membrane, the less air will get through. This is an inverse relationship, so it goes on top of the fraction instead of on the bottom. We're going to measure the thickness in centimeters. Okay. I know a lot of people who watched the previous video are going to be shouting at their screen saying, "Cancel the centimeters." If you are one of those people, then I think you missed the point. We saw that quantities like fuel efficiency and the Hubble parameter could have their units simplified, and that sometimes led to interesting results. But that doesn't mean we should simplify them. It's way more intuitive to measure fuel efficiency in gallons per mile than in square millimeters. And for the Hubble parameter, kilometers per second per megaparsecs is a direct description of how it's measured. At the end of that video, I mentioned that I used nanometers per square root nanometer in a research paper, and a lot of commenters suggested writing it as just square root nanometers, unironically. Yes, it's certainly interesting that you can write it as square root nanometers, but actually writing that in a research paper would be silly. I was trying to describe a relationship between two lengths, so why would I obscure that relationship by cancelling those lengths?
I showed you my my program, right? let me pick it up again here. Where we very often can, for example, see something like this and just write, by the push of a button, write simplify, because it makes it somewhat easier to look at, right? You get essentially this instead of that. Like, it's the same shit. It's basically the same thing, but like, I guess it's a bit more pleasing to the eye. But the thing is, as I said in the very start of the video, is complexity sometimes is important to maintain, because you can push simplification to a certain degree and you lose track of what you were actually intended to do.
It's fun to play around with units, but in practice, you should always use the units that best describe the physical quantities that they represent. Usually, it's the most commonplace units that are the ones that are best at doing this. The only exception being kilowatt hours per 1,000 hours, which is an inexcusable abomination. So no, we're not going to cancel the centimeters. You can do that in your own time, but right now we're building a sensible unit for sensible people. Right, the next thing to consider is pressure. If we increase the difference in air pressure between the two sides of the membrane, more air will get forced through. This turns out to be a linear relationship, so we need to put pressure on the bottom of the fraction. Now, the CGS unit of pressure is the bary, not to be confused with the bar, which is a million times bigger, but we're not going to use either of these,
not
or the
Pascal
SI standard
either.
Pascal, because this is a sensible unit for sensible people. So we're going to use the only sensible option, centimeters of mercury.
Dumb.
What is a centimeter of mercury, I hear you ask? It's the amount of pressure that will push liquid mercury 1 centimeter up a tube. Great.
Olden days.
This unit is a holdover from that time in history when we used mercury for basically everything, before realizing that it's both toxic and volatile.
Yeah.
The best combination of properties. And finally, moles. We don't like moles. Moles are silly, so let's replace them with centimeters cubed STP, the number of air molecules that fill a cubic centimeter at some standard temperature and pressure. Oh, and multiply everything by 10 to the minus 10. This is the bara, a unit of gas permeability used in the study of membranes, particularly contact lenses. And I had to check through some research papers to make sure that this unit is actually used, because when I first heard about it, I was certain it had to be a joke.
This is why I said that you should not dive into the field of optics. This is why people don't care about such things as lumen. They barely touch these things. That's why everything is just reliant on like manuals that they have down. Because who the hell wants to derive this? I'm being facetious here, but wow, this truly is cursed.
It contains 4 different variations of centimeters, 2 of which aren't even related to length. And centimeters of mercury isn't even the most common unit of
Millimeters.
mercury. It's way more standard to use millimeters of mercury.
Yeah.
Which would be called torrs if they were the same thing, which for some reason they aren't? I've intentionally avoided talking about joke units like smoots or beard seconds in this video. I'm not just going to repeat Jan Mieseli's A Joke About Measurement. No, the whole point of this is to understand how we use units in practice, in the real world. And this monstrosity is a real unit used by real people. That being said, I do genuinely think the bara has its place. If it were completely absurd, people wouldn't use it. The main reason the bara is so complicated is that permeability is related to a lot of different factors. Sure, using centimeters of mercury and cubic centimeters STP is weird and esoteric, but even if we replaced everything with SI units, we'd still have something pretty cursed. Notation standards only make up half of the cursedness. The other half is the complexity of the science itself. There are so many other interesting ways units can get frighteningly bizarre that I haven't touched on yet, so there may be a Cursed Units Part 3 in the distant future. Maybe then I'll finally talk about Imperial units. For now though, I'm just going to go ahead and crown the Hubble parameter and the bara as the king and queen of cursed units, and then go and hit my head against a rock for a while.
Most people in the rest of the world, beside, I guess, the UK and... No, even Canada decided to not be so stringent with using empirical units and switch to hours. Like, you know, the system is very bad when even criminals are making use of the metric, like they are buying kilos. But yeah, like the rest of the world's just rejoicing for part 3. Yes, we're finally getting to make fun of the others. Oh, please don't hate me. Man, this was great. This is how cursed things turn out to be. And the one thing that I'm always glad about is that there were people way before myself who paved the way for the understanding of these kind of things, who actually did the math to make sure that most of us just would have to memorize certain things and just course through it. Because I would not love to be the person who decides to bear the cross of making a very, very complex unit mine. But anyways, guys, thank you so much for checking this out. Thank you, Joseph, for making this awesome video. A great reminder for myself to also be aware of some of the notations that I have made in the past that may or may not have been wrong. But guys, please do make sure to go and subscribe to Joseph. I especially like the video. It definitely will help him to make more of this type of content. And of course, if you like the reaction, like and perhaps also subscribe if you want to see some more reactions from this channel. But that being said, wish you all to have a wonderful day. For those of you who may be starting in university or just high school in the coming months, please do make sure to have your dimensional analysis down. It will save you a lot of time. Alright, bye.